In the previous video, we looked at the definition of a tree and also the concepts that go with it. Uh, Things like the definition of a node being the parent of another node or two nodes being siblings and so on. Now, in this video, what I'm going to talk about is again about the concepts and definitions, but this time we are going to look at a special kind of tree, which is called a binary tree. We will talk about the implementation in C++ a little bit, and we will see some pseudocode for a couple of functions that work with binary trees in this video. But in later videos, we will go more in depth in terms of implementation, and we look at that more closely. So what is a binary tree? A binary tree is a tree that every node is allowed to have either 0, 1, or 2 children. So a tree where every node has at most 2 children, hence the name binary, right? Now, before moving on with more definitions and ideas, let's make sure that we understand this concept by doing a couple of examples. So, for example, A, B, C, D, E, F. This tree is a binary tree because if you look at the node, this node has 2 children, B has 2 children, C has only 1 child, and then D, E, and F have no children at all. So 0, 1, or 2 children for each node, that's perfectly fine. So it's a binary tree. Another example would be this, for example. Again, this is a binary tree because A has 1 child and B has no children. Everything is fine. So that is also a binary tree. Another example would be something like this. Again, A has only 1 child, B has only 1 child, C has only 1 child, and D has no children. So this is also a binary tree. Another good one, and we will see later on that we want our binary trees to be ideally balanced. And this is not balanced at all because everything is on the left side. But according to the definition, it's a binary tree because every node has either 0, 1, or 2 children. Okay? An example of a tree that is not binary would be something like this. Now, here, obviously, B has 3 children, which is not allowed, so this is not a binary tree. Okay, so now that we know what a binary tree is, the first thing that I want to tell you about a binary tree is, since every node has at most 2 children, to be able to talk about the children in an easier way, we call them left child and right child. Okay, so for example, here at node A, the left child of A is B and the right child of A is C. And for C, for example, the right child is F, but it doesn't have a left child, and so on and so forth, right? So left child and right child, we are going to use this terminology a lot. The other thing that we have is what's called left subtree and right subtree. Okay, so for example, if we look at the node A, the left subtree of A is everything that is on the left side, and the right subtree of A is everything that is on the right side. So this is called the left subtree, and this is called the right subtree. And it doesn't have to be at the root. At every node, we can talk about that node, the left subtree and right subtree. Okay? For example, if you look at B, the left subtree of B is this. So this is the left subtree of B. And then the right subtree of B is empty. So here I should say left subtree of A and right subtree of A. Okay? So left and right subtrees, when we are defining these functions that work with binary trees, we are going to use this idea of left and right subtrees a lot. So that's an important concept as well. Now, in terms of implementing this in say C++, you can see that there are similarities to linked list because you have a node and then that node is connected to other nodes. But as I said here, every node here potentially can be connected to two nodes, left and right children. Okay, so instead of having a next pointer at every node or a next and previous pointers at every node, what we have here is that every node contains some kind of key or data, and then it has two pointers to other nodes. One of them is called left, that points to the left child of that node, and the other one is right, that points to the right child of that node. Okay, so visually, the structure of a binary tree in C++ will be something like this. You have the root node, okay, that has some data, let's say 7, and then 2 pointers, right? It's the previous and next, like a double linked list. Here, this one is called left, and this one is called right. Okay, so left points to another node, and right points to another node. Okay, so another node structure here that has, again, some value, 5 and 2 pointers. And same on the right side. So 10 pointer. Okay, and it could be that we didn't say that every node must have exactly 2 children. It could be that a node like this, for example, this one has a left child but no right child. So in that case, the left pointer points to a node, which is the left child of this node that contains some data and some pointers, and the right pointer, because we are assuming that this node doesn't have a right child, is going to be a null pointer. Okay, and similarly, if a node has a right child but no left child, then the left pointer is going to be null and the right pointer will point to another. And 12 pointer. Okay, and in particular, if you talk about the leaf nodes, the leaf node is a node, if you remember from the previous video, is a node that doesn't have any children. So no left child, no right child. So both of these pointers will be null if this is a leaf node, and similarly for this one. Okay, so you can see that with this structure, we can represent a binary tree in a very nice way in C++. Okay, now if I want to show you how this is done in C++, you will have a class called binary tree, for example. And then there are some public members that, the functions that we will talk about in later videos. But then in the private section, what you need, similar to linked list, what you need is you need to define what a node is. So in this section, we can define another class that I'm going to call tree node. And according to what we see here, a tree node has 3 member variables, some key or data, and then 2 pointers to other tree nodes. So there will be some data of type T. I'm using templates. I'm assuming that I'm using template. And then 2 pointers. So the type of those other 2 member variables will be tree node star called left. So this is the pointer that points to the left subtree or left child, I should say. And then tree node star right that points to the right child of this node. And similar to, again, if you remember, similar to linked list, we might want to have a constructor here that creates a tree node. So it takes some value of type T, named D, and then it initializes data with D, and it sets left and right pointers to null. So left is null, and right is also null. And that would be it for the constructor. Okay, so empty body, and that will be the definition of the tree node class. So it's a very simple class. And since we use tree node only in the context of binary trees, I define this class inside the definition of the binary tree class because I'm not going to use objects of um, this class in any other context other than the creating a binary tree. Okay. Now, if you remember again from the linked list class, we had only one member variable. We said that in a linked list, the only thing that you need to know about the linked list is the address of the first node, because then from the first node, you can find out where the next node is, and then from that node, you can find out where the third node is, and so on. So because of that, we had only one member variable, which we called head, right? Now, a similar story here. If you want to access every node in a tree, the only thing that you need to know is you need to know where the root node is, because from the root node, you can find out the address of the left and also the address of the right child. And then from the left child, you can find the left and right children of that, and then so on and so forth. So if I tell you where you can find in the memory the root node, then that would be enough information to access every other node in the tree. And because of that, again, similar to linked list, here we are going to have only one member variable, which is a pointer of type tree_node. So tree_node star that we can call root. And that will be it. I mean, by it, I mean in terms of the member variable, but obviously we need member functions to add functionality and do computations with binary trees. But that's the idea. So only one member variable. And in the picture, that will be not a node, but just a pointer that I'm going to put here. This is the root, and it's a pointer, so it doesn't have any data, right? Just a pointer that points to the root node that contains the top value and pointers to the left and right children. Okay, so as I said, we will type this in a project and implement functions in later videos, but this is just for conceptually understanding how this will be implemented. Now, I want to introduce a couple of definitions here in this video. One of them is the size of a binary tree. And that's a very simple definition. It's just the number of nodes. So for example, this binary tree here has 1, 2, 3, 4, 5 nodes. So we say the size is 5. If we go to here, the size of this binary tree is 1, 2, 3, 4, 5, 6. The size of this one is 2, this one is 4, and so on. So that's the first definition, size. Later on, we are going to learn how to compute these uh, given the code for a binary tree. But for now, it's just the definition. So size of a binary tree is the number of nodes in that binary tree. Very simple. The other definition, which is also simple, maybe not as simple as size, is the height of a binary tree. Okay. Now, here's the definition. The height of a binary tree is the number of edges in a longest path from the root to a leaf. This is the definition of height. Okay. Now, let's do some examples for the height because it's not as trivial as size, right? So the first tree that I'm going to look at is this binary tree here. Okay. You want to compute its height. So it says the number of edges in a longest path from the root to a leaf. Now we have 2 or 3 leaves, I should say, 3 leaves here, and root is 1 always. Now we have to look at the paths from the root to every leaf. So the first one is this path here in blue that has only one edge, consists of one edge only. Now changing color, the path from A to the other leaf, which is C, in red will be from A to B and then from B to C. So now this path consists of two edges. And finally, the path from A to the last leaf, which is D, I'm using purple for that. So from A to B and B to D, this path also consists of two edges. Now we have two longest paths. That's why I say a longest path. And the number of edges in both of them is 2. So we say that the height of this tree is 2. So height equals 2. Another example. Okay. So you want to know what is the height of this tree? Again, the root is labeled with A, and leaves, C is a leaf, D is a leaf, H, and G. So we have 4 leaves. So I have to look at all the paths from the root to each leaf and count the number of edges in each one of them. And then the highest one is the height. So from A to C, we have the path from A to B and B to C. So that's 2 edges. Okay. The next one is from A to D. D is my second leaf. So from A, I have to go to B, and then from B to D. So that's also 2 edges. Then the next leaf that I'm going to look at is H. So to get to H from the root, I have to go from A to E, and then from E to H. I'm using orange for that one. That path also consists of 2 edges. And finally, my last leaf is G, right? And the path from the root A to G is from A to E, E to F, and F to G. And that one consists of 3 edges. So we say that the height of this binary tree is equal to 3. Okay? Now, this should be clear by now, but there are special cases that I think it doesn't hurt if we look at them as well, because in particular, one case will be confusing later on. So another example is this binary tree with only 2 nodes, A and B. So A is the root, there's only one leaf, which is B, and the path, there's only one path from the root to a leaf, which is this path here, which consists of one edge only. So the height of this binary tree is 1. So it takes traversing only one edge to get from the root to the leaf. Okay? Now, even simpler than this is a binary tree with only one node, A. Now, in this case, you can argue that A itself is the root and the leaf, right? Because it doesn't have any incoming edges, so because of that, it's the root. And it doesn't have any children, so because of that, it's the leaf as well. Now, how many edges do I need to traverse to get from A to itself? And obviously the answer is no edges. I don't need to traverse any edges to get there. So the number of edges in that path is 0. In other words, the height of this tree is 0. Okay. Now later on, as I said, we will look at implementation, first pseudocode and then implementation of these functions, height and size, and other functions as well that can be put in the public part as member functions of this class binary tree.